back. In this video, we're going to extend your knowledge of unit analysis to the two systems of measurement, which we're going to focus on, which is the US customary system and then the metric system. So we are going to look at standardized unit systems, which, the word standard in general just means to keep everything the same for everyone. Like you may have heard of standardized test scores. If you've taken the SAT or the PSAT, they take your score and they standardize it so that they can compare your score and your performance to the performance of others. So here we're kind of doing the same thing with our systems of measurement because, as you can see, different units of measure equal other units of measure. So for instance, you've got in the US customary system, we have all these different things we have to memorize. So 1 inch is equal to 2.54 centimeters. 1 foot is equal to 12 inches, and so on. You've got equivalents for yards, rods, fathoms, furlongs, miles, a nautical mile, and a league. It's a lot to remember. And then we also have the weights for the US customary system. So it's broken down into these three different groups. You've got this group it's pronounced avoirdupois, and it's based on 1 pound being equal to 16 ounces. And then you have your other equivalents, and then you've got the troy system of weights, which originated back in England around the 15th century. And you can see units like pennyweight, troy ounce, carats, and so on. And then apothecary was used for pharmacy, for dispensing medications. So you have those there. And then you also have volumes, liquid measures, and dry measures. So this chart will be very useful to you as we're doing these problems. So let's take a look at the first problem where it tells us that the length of the Kentucky Derby horse race is 10 furlongs. How long is the race in miles? All right, so if I go back and I look, I can see that 1 furlong is equal to 1/8 of a mile. So I'm going to write that down here. And if you don't want to deal with a fraction, that's fine. We can change fractions to decimals, right? So if I just pull up a calculator like Desmos, and I want to change 1/8 to a decimal, I can just do 1 divided by 8, which is 0.125. So that's its decimal equivalent. So we can also say that 1 furlong is equal to 0.125 miles. Okay, so here I'm trying to find out how long the Kentucky Derby race is in miles, but it tells us that's in 10 furlongs. So we're going to use unit analysis, which we talked about in our last video. So you've got 10 furlongs, and I'm going to take my equivalent here, which is 1 furlong equals 0.125 miles. And remember, we want furlongs to cancel out. So I'm going to put 1 furlong in the denominator, and then I'm going to put 0.125 miles in the numerator. And now the furlongs are going to cancel, and all we have to do is just multiply straight across. So you would just multiply 10 times 0.125, which anytime you multiply by 10, it really just moves the decimal one place to the right. So it's just going to be 1.25 miles. So that's how long the Kentucky Derby race is in miles. Because furlongs is not something that we typically use a lot. So miles is a little bit more comprehensible. I'm going to let you try to check your understandings on your own. So you can always pause the video and try those. If you have questions, you can always reach out. Okay, so that was just a little glimpse at using the US customary system. We also have the international metric system. So for those of you that maybe have lived overseas, this will be familiar to you. It replaces the many customary units that we need to remember. There's really not as much memorization involved here because it's based on a decimal base 10 system. So here we can see the different prefixes like deci, The abbreviation is D, centi is C, milli is M. And then you've got micro, which is use this Greek symbol mu, or you may see MC instead. A lot of times that will be seen in like pharmaceutical calculations. And then you've got nano, which is N, and then pico or pico, which is P. Okay, and as you notice, as I go down the list, the smaller and the smaller and smaller it gets. Okay, you also have larger values, which are deca, which is DA, hecto, H, kilo is K, mega is capital M, giga is capital G, and tera is T. You may have seen these like with storage on devices like megabytes, gigabytes, terabytes. All right, so let's say I want to convert 275 centimeters to meters. All right, so when I look, I can see that 1 centimeter is really equal to 10 to the negative second meters. And 10 to the negative second is really 1 over 10 to the second, which is 1 over 100. So 1 centimeter is equal to 1/100th of a meter. Okay, so what I can do is I can multiply both sides by 100 to cancel the hundreds out, and 100 times 1 is equal to 100. So I know 100 centimeters is equal to 1 meter. Okay, that's my conversion that I can use. Now I can show you a trick to kind of remember that. So there's like a sentence you can use, and it is King Henry died, and then from drinking chocolate milk. And the K stands for kilo, the H stands for hecto, the D stands for deca, and then you've got your units. So it could be like meters, liters, grams, and then you've got deci, centi, milli. So if I wanted to convert, for instance, like here, I want to know 1 meter equals how many centimeters. Meters is here in the middle, centimeters is here. So if I'm here and I have to get to here, I would just move my decimal point 2 places to the right. So I would know that if I take the number 1 and I move the decimal point 2 places to the right and fill in zeros, you get your 100. So 1 meter equals 100 centimeters. Let's say I had like 0.2 centimeters equals how many meters? Okay, let me slide that down. So let's say I want to go backwards now. So I'm at centimeters and I want to go to meters. I would go 2 places to the left. So I'm going to take my decimal point and move it 2 places to the left and fill in a 0. So I would know that 0.2 centimeters is actually equal to 0.002 meters. So that's just a quick way that you can remember to how to convert using the metric system. Okay. And that's not including the micros, nanos, picos, or megas, gigas, teras. That only works for the deci, centi, milli, deca, hecto, and kilo. All right, so here we have our conversion. So now this is real easy. I'm just going to take 2759 centimeters, and I know that 1 meter is equal to 100 centimeters. And again, I'm putting centimeters in the denominator because I want them to cancel. So here I have 2759 times 1, which is 2759, divided by 100. And anytime you divide by 100, you're just basically moving the decimal 2 places to the left. So it's just going to be 27.59 meters. In letter B, we're asked how many nanoseconds are in a microsecond. Okay, so we know that nano is larger than micro, right? So I'm going to divide the longer by the shorter. So I've got 1 microsecond divided by 1 nanosecond. So here I've got 1 microsecond is 10 to the negative 6th seconds, and 1 nanosecond is 10 to the negative 9th seconds. Okay, and of course my seconds are going to cancel out, which is what I want because I'm looking for how many nanoseconds are in a microsecond. And I'm going to divide 10 to the negative 6th divided by 10 to the negative 9th. So if you'll remember, when you divide, these things are called bases, the tens. When we divide like bases, you subtract the exponents. So really what I have is 10 to the negative 6th minus negative 9. And two negatives turn into a positive. So this is really 10 to the third. Negative 6 plus 9 is 3. And 10 to the third is a 1 with 3 zeros. So there's actually 1,000 nanoseconds in 1 microsecond. Okay, and an easy way to remember that is we're always going to divide the longer by the shorter. So 10 to the negative 6th is larger than 10 to the negative 9th. All right, for the next one, we need to fill in the blank. 1 terabyte is blank times as much as 1 kilobyte. So basically, we're going to be doing the same thing that we just did. Okay, so if I look at my chart, I know that 1 terabyte is 10 to the 12th bytes. And I know that 1 kilobyte is 10 to the third bytes. So again, I'm going to divide the larger, which is a terabyte, by the shorter, which is a kilobyte. So I've got 10 to the 12th divided by 10 to the third. And you're dividing like bases. Remember the tens are the bases, so we subtract the exponents. So really it's 10 to the 12 minus 3, or 10 to the 9th. And 10 to the 9th is a 1 with 9 zeros, which is a billion. So 1 terabyte is 1 billion times as much as a kilobyte. A square meter is blank times as large as a square centimeter. Okay, so now we're dealing with square. And we already had learned before, right, that 1 meter equals 100 centimeters. Okay, so let's write that down. Now I'm trying to figure out how much a square meter is equivalent to in centimeters. So if I need to find square meters, I'm going to square that side. And since it's an equation, whatever you do to one side, you have to do to the other. So I'm going to square the other side as well. And 1 squared gives me 1, and meters squared is meters squared. So you've got 1 square meter equals, now I'm going to take 100 squared, which is 100 times 100, or 10,000 centimeters squared. So 1 meter squared is equal to 1,000 centimeters squared. So a square meter, 10,000. So a square meter is 10,000 times as large as a square centimeter. Here's some conversions from metric to the US customary system. So in case you've ever, had something in inches and you need to convert it to centimeters, 1 inch is actually 2.540 centimeters and so on. So here's another list of conversions. again, converting from customary to metric. And then on this side, you've got metric to customary. Okay, so I'll give you an example here. And then I'll have you guys try B on your own. You've got a marathon running race is about 26.2 miles. About how long is it in kilometers? So if I look, I can see that 1 mile is 1.6093 kilometers. So let's write that down. Okay, so I'm going to use unit analysis. I'm trying to convert 26.2 miles to kilometers. So I'm going to multiply by my conversion right here. We just need to make sure that the miles cancel because we need to be left with kilometers. So that just means I need to put the 1.6093 kilometers in the numerator and the 1 mile in the denominator. And my miles cancel, and now I just multiply straight across 26.2 times 1.6093, and it's 42.2 kilometers. So if you were running a marathon, which typically is 26.2 miles, if you were running that in Europe, you would, or any other country that uses the metric system, Canada, it would be 42.2 kilometers long. So that's the kilometer equivalent to miles. Now we also have different temperature scales. We've got Fahrenheit, Celsius, and we use Kelvin in science a lot. So we can see the different boiling points here. For instance, water boils at 212 degrees Fahrenheit, but it's really boiling at 100 degrees Celsius. And in Kelvin, it would be 373.15 Kelvin. Notice that Fahrenheit and Celsius have the degree symbol. Kelvin does not, okay? You can see that water freezes at 32 degrees Fahrenheit, 0 degrees Celsius, and 273.15 Kelvin. And then we have what's called absolute zero, which for Fahrenheit would be negative 459.67 degrees Fahrenheit, negative 273.15 degrees Celsius, and 0 Kelvin. So if I wanted to look at a little conversion here, right? Let's say I want to look at the boiling temperature. I can see that, like, how are Celsius and Fahrenheit related to each other? I can see that for Celsius, you've got 100 degrees Celsius minus 0 degrees Celsius equals 100 degrees Celsius, boiling. So that's the difference between the water boiling for Celsius. For Fahrenheit, boiling is 212 minus freezing, which is 32, and that would give me 180 degrees Fahrenheit, and that's freezing. So each Celsius degree is basically 180 over 100 Fahrenheit degrees. If I take those two comparisons. And 180 divided by 100 is 1.8. The Fahrenheit degrees. So what that means is, if I wanted to convert, let's say, something in Celsius to Fahrenheit, I would just multiply the degrees in Celsius by 1.8, because it's 1.8 times, plus 32, and that gives me my Fahrenheit. Here's a quick little table you can use with different conversion formulas. So if I want to convert to Celsius, if I know my Fahrenheit temperature, I could just subtract 32 and then divide by 1.8. If I want to convert to Kelvin and my temperature's in Celsius, you could just add 273.15. And if I want to convert to Celsius and I have my temperature in Kelvin, I could just subtract 273.15. So the average human body temperature is commonly quoted as 98.6 degrees Fahrenheit. What is this temperature on the Celsius and Kelvin scales? Okay, so I'm given my temperature in Fahrenheit and I want to convert to Celsius, right? So I'm going to use the formula Celsius equals Fahrenheit minus 32 divided by 1.8. So here I'm just going to substitute 98.6 for F and then subtract 32 and divide by 1.8. So the first thing I'm going to do is take care of the numerator, which is 98.6, and then I'm going to subtract 32, and I end up with 66.6 just for the numerator, and then I'm going to divide by 1.8, and 66.6 divided by 1.8 is 37.0 degrees Celsius. So that would be the average human body temperature in Celsius compared to our 98.6 degrees Fahrenheit. Okay, I also want to convert to Kelvin. So for Kelvin, I'm going to take now the Celsius temperature that I just found, and I'm going to substitute it in. So Kelvin is equal to Celsius plus 273.15. So I know that 98.6 degrees Fahrenheit is 37 degrees Celsius. So I'm going to do 37 plus 273.15. So in Kelvin, the average body temperature would be 310.15 Kelvin. Let's look at units of energy and power. Like, first of all, what is the difference? So power is measured in watts, W-A-T-T-S, and power is the rate at which energy is used. Okay, what is energy? Energy is measured in joules, and it's what makes matter move or heat up. And then a conversion that might be of use to you is 1 watt is actually equal to 1 joule per second. Okay, I'm going to do the check your understanding here with you all so you get a little practice. As you ride an exercise bicycle, the display states that you are using 500 calories per hour. Are you generating enough power to light a 100 watt bulb? So 1 calorie is equal to 4,184 joules. So we know we're going to be using that. All right, so what do we know here? We've got 400 calories per 1 hour. Okay, and to convert this, right, I want to convert this to see if we are generating enough power to light a 100 watt bulb. So it should be in joules per second, right? Because that's what I learned, that 1 watt is 1 joule per second. So I want my final answer to be in joules per second. So I know 1 calorie is equal to 4,184 joules. Okay, so I know that the calories are going to cancel out now. Okay, and then I also know that there's 1 hour and there's 60 minutes in an hour. So my hours are going to cancel. Okay, so calories canceled, hours canceled. Now remember, I need joules per second. So how would I change minutes to second? Well, I know that in 1 minute, there's 60 seconds. So now my minutes will cancel, and I'm left with joules per second. So I would just multiply straight across on top, 500 times 4184 times 1, and then I divide by 60 times 60. So let's see what we get here. So it's going to be 500 times 4184 in the numerator. And then I'm going to take the denominator. And now I'm just going to divide both of them. So in the numerator, it will be 2,092,000. And I'm going to divide that by 3,600. And I get 581 joules per second, approximately. Okay. So at some point in your life, you may have to look at an electric bill and interpret that. And electric utility bills, electrical energy is measured in kilowatt hours. And for your interest, 1 kilowatt hour, its conversion is 3.6 million joules. Okay, and you can always look all of this up, by the way. So let's say your utility charges 15 cents per kilowatt hour of electricity. How much does it cost to keep a standard 100-watt light bulb on for a week? How much will you save in a year if you replace the bulb with an LED bulb that provides the same amount of light for only 25 watts of power? Okay, so the first question we need to find out is, how much energy does the bulb use in 1 week, right? We're looking at this portion of the question here. Because in order to figure out how much it's going to cost, we need to know how much energy the bulb uses in a week. Okay, so what do I know? Well, I know that it's 100 watts. And I know that 1 kilowatt in 1 kilowatt, there's 1,000 watts. Okay, how do I know that? Well, again, there's a couple ways you could look at this. You can go back to here. You can see that kilo means 1,000. You can also use the little, helpful little tool here. Like here's kilo, hecto, deca, and then the unit. So I know that there's 1 kilowatt in 1,000 watts. All right, so back to this. So I know that I'm looking for how much energy the bulb uses in a week. So I got to make sure I incorporate 1 week there. And then what do I know about weeks? Well, I know that there's 7 days in 1 week. So right now, my watts are canceling, my weeks are canceling. Okay. And I want my days to cancel because I need it in kilowatt hours. So what do I know about 1 day? There's 24 hours in 1 day. And now my days will cancel. And now I'm left with the units I want, which is kilowatt hours. So you're just going to multiply straight across and then divide by 1,000. So 100 times 7 times 24 divided by 1,000. and you should get 16.8 kilowatt hours. Okay. Now, we didn't really answer the question yet, though, because it says, how much does it cost to keep the 100-watt light bulb on for a week, right? So now I need to find the cost. And I know that it's 16.8 kilowatts hours. And they're charging, and the problem, it tells us 15 cents per kilowatt hour. So that's 15 cents, and then per, remember, means divide. So we're dividing by kilowatt hours, and as you can see, the kilowatt hours are going to cancel out, which is what we want because we're looking for cost, which should be in dollars and cents. So if I multiply 16.8 times 0.15, I get 252, and that would be in cents. So it's really $2.52. Okay, so that would be the cost. Now, we answered the first question. The second question says, how much will you save in a year if you replace the bulb with an LED bulb that provides the same amount of light for only 25 watts of power? So if you replace the 100-watt bulb with a 25-watt bulb, 25 is 1/4 of 100. So that just means that you're going to be using a quarter as much of the energy, okay? So what I'm going to do is I'm just going to take the $2.52 and we're going to multiply that by 3/4 because you're using a quarter of the energy. That means that there's 3/4 left over. So 3/4 times 2.52. There's a couple ways you could do that. You could either do 3 times 2.52 and then divide that answer by 4. Another way you could do it is just change 3/4, 3/4 to a decimal. So 3 divided by 4 is 0.75. And then multiply that by 2.52 and you get 1.89. Okay, so this is equal to $1.89, and that would be, of course, per week. So we figure in a year you're going to save about 52 times that, since there's 52 weeks in a year. So how much are you saving? Well, it's $1.89 a week that you'll be paying. And we know that there's 52 weeks in 1 year. So I know weeks are going to cancel, and $1.89 times 52 is about $98 per year. So if left on the entire time, which we know that that would not be the case, right? The more efficient bulb would save about almost $100 per year. Okay. Let's next look at density and concentration. So what's the difference? Density, think of that as like it describes the compactness or crowding of an object. An example of that could be like the density of water, which is 1 gram per cubic centimeter. So objects with densities less than that will float. Objects with densities more than that will sink. And then concentration describes the amount of one substance that is mixed with another. An example could be concentration of an air pollutant, medicine dosage, blood alcohol content, which is abbreviated BAC. Manhattan Island has a population of about 1.6 million people living in an area of about 57 square kilometers. What is its population density? So, in other words, how compact or crowded is it? If there were no high-rise apartments, how much space would be available per person? So let's first figure out what the population density is. In other words, we're looking for like how many people per square kilometer. So I'm going to be dividing here. I know that the population is 1.6 million. So that's 1,600,000. And I'm going to divide that by the area of Manhattan, which is 57 kilometers squared. So if I divide 1.6 million divided by 57, we get about 28,070. So we'll round that to like 28,000 just to make it easy. So it's about 28,000 people per square kilometer, right? So picture a square that's 1 kilometer by 1 kilometer. There would be 28,000 people in that little space, okay? So that's the population density. The second question is, if there were no high-rise apartments in Manhattan, how much space would be available per person? So think about how much space the high-rises save, right? If they didn't exist, how much space, in other words, how much area would each people get? Like, what would be your property? So I would need to take my a conversion here, and my conversion is the answer I just found. I've got 28,000 people, and that's equal to 1 square kilometer. So I'm going to write 1 kilometer, 1 square kilometer over 28,000 people. Okay, now what's my conversion for kilometers? Well, I know that 1 kilometer equals 10,000 meters, right? So I would need to put kilometers on the bottom. The problem is I've got square kilometers, but it's really not a problem. It's no big deal because we learned that if we want to convert to square kilometers, you just square everything. So now we're just going to square everything. So now what I really have is 1 square kilometer per 28,000 people. And I'm going to multiply that by 1,000 squared, which is 1,000,000. So that's meters squared over, and 1 squared still stays 1. It's just 1 square kilometer. So now the square kilometers will cancel out. So you might have been wondering, like, okay, why did he put the 1 square kilometer on top and the people on the bottom? And it's because I'm just trying to figure out in meters, like how many square meters one person can fit in. So here you've got, let's see, 1 million divided by 28,000. And if I get a rough estimate for that, it comes out to about 36 square meters per person. Okay. So what exactly does that mean? It means that if Manhattan had no high rises, each person would have only about 36 square meters, which is equivalent to a room that's 6 meters. So like a meter is basically about 3 feet. So, if you think of 6 meters, right, it's roughly 18 feet on a side. So picture a room, that's like 18 feet by 18 feet. That's all you would have if there were no high rises. So that is really, really small. That is not a lot of space. Like that is your space only to live in. Okay. And that doesn't include space for roads, schools, etc. So it's probably even smaller than that. This is a rough estimation. The last one I'm going to give you all a chance to try. So here you're converting, and again, you have those conversions that you can use that are up here. So please don't forget, you have all these conversions here, the tables that you can use to figure it out. I will give you the answers for the last two though, so you can check your answer. So for A, you should get 225 milligrams, and for B, you should get 9 milliliters. And anybody that is, maybe going into nursing or pharmacy or doctor, this problem here, A and B, will be practical and useful for you. So that is the end of the video. If you have any questions, please reach out to me. I'm happy to help. Enjoy the rest of your day.